Professor Dave and Chegg here. We know how to reduce carbonyl-containing compounds like aldehydes and ketones down to alcohols. But what if we want to remove the oxygen atom entirely and reduce all the way down to the alkene? There is a good method for doing this called the Wolff-Kishner reaction. Let's learn about it now.
As we said, the Wolff-Kishner reaction is a reduction, and the reduction is performed by a hydrazine, which is a functional group involving two adjacent nitrogen atoms, and the chemistry that occurs will be very similar to the mechanism for imine formation. One of the nitrogens from the hydrazine will attack the carbonyl carbon, and we'll go through all the steps we already know from learning about imine formation, kicking off water to get to this intermediate. The only difference is that instead of an imine, we will call this a hydrazone, because the nitrogen participating in a double bond to carbon is also connected to another nitrogen, so it is a different functional group. Now, hydrazones are in equilibrium with a tautomeric form, the diimide, and this equilibration is catalyzed by base. Notice the additional proton on this carbon in the diimide tautomer, as well as the double bond between the nitrogens. Then the slow step for this reaction is the deprotonation of the diimide by the strong base. This leads to loss of nitrogen gas and the formation of a carbanion, which is an especially reactive species. The lifetime of a carbanion in a protic solvent is extremely short, and protonation by the conjugate acid of the base used in the previous step leads directly to the alkane. So, as we can see, this is an excellent method for reducing an aldehyde or ketone down to an alkane, thereby removing oxygen functionality altogether. And because nitrogen gas leaves solution once formed, this simplifies the process of isolating and purifying the target molecule. Indeed, it is the thermodynamic stability of the N2 molecule that is a primary driver of this reaction.
With that, we have another transformation in our synthetic toolkit, the Wolff-Kishner reaction. Professor Dave for Chegg. See you next time.